Welcome to Unit 9, Inference for Quantitative Data, Slopes. This is Topic 9.4, Setting up a Test for the Slope of a Regression Model. In Topic 9.5, we're going to actually carry out a test for the slope of a regression model. So in this topic, we're just going to kind of set everything up, pretty much steps 1 and steps 2 of the test process, and make sure you understand exactly what the test is all about. And then 9.5, we'll actually go ahead and fully carry it out. All right, so what exactly is a test for slope? Well, understand that we have already learned how to run a z-test for a proportion and a t-test for a mean. The idea in both tests was fairly simple. A problem told us what the true population parameter is, whether it be a proportion or a mean, and we wanted to test a claim that the true parameter was either lower, higher, or simply different than what we were told. The idea was that there was a claim made. Somebody said, I believe that more than 20% of jelly beans are orange. Okay, I guess we got to prove that somehow. Or somebody said, I think the average weight of all kangaroos is more than 400 pounds. Okay, great. Now we just have to find a way to test that. And that's exactly what a significance test is that we learned about with the z-test or a t-test. So to show significant evidence that our claim is true, if you remember, we had to start with a sample statistic, whether it be a sample proportion or sample mean. If we want to show that more than 20% of jelly beans are orange, I guess we better get a sample and get a sample proportion. And if we want to show that the average weight of kangaroos is more than 300 pounds, I guess we better get a sample of kangaroos and get a mean weight, and hopefully it's going to prove it. So then we have to build the sampling distribution for the statistic, assuming the null hypothesis is true. Remember, a single sample all by itself really doesn't tell us a whole lot. We need a sampling distribution to show us all possible sample means or all possible sample proportions. That way we can see where our sample fits in. Is it significant or is not? Once we have that data, once we see where our sample statistic falls into the sampling distribution, then we can see whether we have significant evidence to prove our claim. Well, we can do the exact same test for a slope. It's simply called a t-test for slope. So we're going to go through the exact same process. There's going to be a hypothesis, a null, an alternative. We're going to have to get a p-value. We're going to have to get a t-score. We're going to have to use TCDF on our calculator. We're going to have to make a conclusion, reject the null, filter reject the null, all that stuff that we've already seen before. In fact, all 4 steps are very, very familiar. Number 1 is naming the test and giving the hypothesis. Number 2 is checking the conditions and building the sampling distribution, assuming the null is true. Number 3 is finding that t-score and the p-value for our sample slope. And then number 4 is making an appropriate conclusion based on the level of significance. Let's make sure we have this idea down pat. I mean, you really, really should understand this idea by now because we've done it countless times. So the big idea here in terms of slope is, now remember, we analyze the relationship between 2 quantitative variables, x and y, found from a sample of n observations. That's how this starts off. We have a set of n observations. We measured 2 quantitative variables, x and y, and we want to explore the relationship between them. The x variable is the explanatory, keep that in mind, and the y variable is the response. The y is what we're trying to predict based on the x with our regression line. So we have a scatter plot of x versus y that showed a linear relationship. If it didn't show a linear relationship, we shouldn't be moving forward at all, obviously, right? So we see this linear relationship between the 2 variables. Then we did some regression analysis to create a linear regression equation with a slope b. Yes, there is the y-intercept as well, but we just don't do any inference with that y-intercept. We focus on inference for the slope, which is the name of this unit. So now usually we get this regression analysis. Again, we could create it on our own if we really wanted to. It does take a bit of work to do that by, kind of hand calculations. We could have our calculator do it, or we could have what's very typical on the AP test is a computer regression output. Now, this computer regression output simply gives us everything we need, which is super awesome. So we really want to focus on that slope, and trust me, a slope will be found. Anytime you throw some data into a computer or into a calculator, you're going to get a slope. Even if the 2 variables aren't related at all, there's probably going to be some type of slope that's going to be calculated because, again, the formula for slope is not one that you necessarily need to know right now, but it is a calculation based on numbers. So if you throw some numbers in a calculator, you're going to get a slope. But the question is, what does our sample slope b tell us about the true slope from the population beta, right? The idea is that we're looking for this true slope of the entire population, not necessarily just our sample. And that slope is beta. And we don't really know what that is, but maybe we have a claim. Maybe we think we know what it is, and we want to test to see if our sample slope shows that or not. You know, it's very similar to us saying, hey, we believe that the average weight of all kangaroos is more than 300 pounds. Okay, well then that's going to be our mu. We're going to say that the null is that it is 300 pounds, and then we need to show evidence it is significantly more than that, which would be our claim or the alternative. So it's a very kind of similar idea here, okay? So let's talk about the steps. The first step is the name, which we already talked about. It's called a t-test for the slope beta. Make sure you give some context. You know, what are we trying to find the slope between? Between the average height of a kangaroo and the weight of a kangaroo, between the number of miles on a car and the price of a car, between the temperature outside and the sales of ice cream on any particular day. You know, make sure you understand that you give some context in that naming of the test. Now, the null hypothesis is that the slope we were told was still true. So understand that that's where we introduce what we call the null slope, okay? And for some kids, it's a little bit tricky to understand, but let me do my best to explain this. So the null slope, again, is this value right here. We're just calling it, I'm just using the symbol null slope, beta with the little 0 there. That's just like what the problem said. So maybe the problem stated, oh, the slope between the temperature on a given day and the ice cream sales on that given day, the slope of that is 5. We think the slope is 5. So for every 1 degree of change in temperature, ice cream sales go up by $5. Okay, that's what we read. That's what we thought was true. So that would be the null, okay? Again, you could compare that to the kangaroo problem where we said, hey, I read that the average weight of a kangaroo is 300 pounds, but I think it's more. So the null mean in that particular problem would be 300 pounds, you know? But again, I don't know what it's going to be for any given problem. That's why I'm just calling it the null slope. And then the alternative is that beta, that the slope is, it's either more than, you know, maybe we think it's more than 5, maybe we think it's less than 5, or maybe we don't care. Maybe we just think that it's something other than 5, it's something different. So again, if you're going to actually do this in a problem, you know, here you'd say, okay, I read that the slope is supposed to be 5. I read the true slope between temperature and ice cream sales is 5. And then, you know, maybe you're like, oh, no way, it's so hot outside. I bet when the temperature goes up, the sales skyrocket. I bet that the true slope is way more than 5. All right, whatever the problem entails, that's exactly how you're going to be talking about the name of the test and the hypotheses. Very similar to what we've done before. All right, but let's talk about this a little bit more, though. All right, let's try to really understand this. In most AP problems, we are simply looking for evidence to support a claim that there is a linear relationship between the two variables. You know, I just mentioned the idea of a slope being 5, and that could come up in a problem. I'm not saying it's never going to come up. But in most AP problems, we're not actually going to give you any number. We're just going to say, is there evidence of a relationship? Meaning, we don't care what the slope is. We just think that there is, in fact, a slope. And here, that would mean that the null hypothesis is that the true slope is 0. Because if there is no relationship between two variables, then that's a slope of 0. As x goes up by 1, y doesn't change at all, showing that the two things or the two variables are not related whatsoever. So if the question doesn't really give you a specific number like 5 or 4 or 14 or -3, whatever, it just says, hey, is there evidence of a linear relationship? Well, then the null is 0. The null is that the true relationship is 0 because the null is what we have to assume. So we're going to assume, no, there's no relationship whatsoever. And the alternative is that, no, there really is a true slope. And that true slope could be positive, which would be greater than 0, which means as x goes up by 1, y goes up by 1. Or that true slope could be negative, which means as x goes up by 1, y goes down as well. And that's the idea in most cases. And I'm not going to say this is going to happen in every problem, because like I said, there could be a problem out there where you're talking about, hey, I thought the slope was 5, and now somebody wants to show that it's more than 5. Okay, it's great. But I'm just trying to tell you guys, in most AP problems that I've seen, you know, they're really just trying to look for evidence of that linear relationship. And in that case, the null is 0. And the alternative is that it's greater than 0, meaning we think there's a positive relationship, or it's less than 0, meaning we think there's a negative relationship. Now, if you don't really care if it's positive or negative, I guess you could use a not equal to sign, but, you know, usually you have an idea in your mind. I mean, if you have these two variables in front of you, if you have a scatter plot, it's going to look positive or it's going to look negative. So you have a feeling of what you want to happen, or what you at least claim is going to happen. So hopefully that makes sense. And if it doesn't, it will make a lot more sense when we start looking at some examples. All right, step 2 is the conditions and building the sampling distribution. So there are 5 conditions here, and as many times as I've seen this come up on AP stats tests, I really rarely see them have you write out all the conditions, but I can't guarantee it's never going to happen, so we do have to go through them. First, the scatter plot of the data has to be somewhat linear. If your scatter plot doesn't show a linear pattern, why would you ever be using a linear regression model in the first place? We have our classic, gotta be a random sample to avoid bias. Next up, we heard this one several times. Our sample does have to be under 10% of the population from which it was drawn to assume independence. Number 4 is that the residuals must be approximately normal. So this is a actual distribution of our residuals. Remember, the residuals are the difference between the actual Y values and the predicted Y values. So we have to make a quick display of those, probably a histogram or a dot plot, just to quickly look at those residuals and make sure there's no major skewness, no major outliers. We just don't want any huge residuals, because if there's a 1 or 2 really, really off residuals, then that means our data is not really as linear as we maybe thought, which could be a bad thing. Number 5, the standard deviation of Y does not vary with X. We want to make sure that the residual plot shows similar variability for each X. I actually mentioned this in the previous videos when we did confidence intervals as well, because we need the same condition met. The idea is that we don't, we understand that our residuals are supposed to be mixed up. Some are going to be small, some are going to be bigger, some are going to be positive, some are going to be negative. We want a mixed-up residual plot. That shows that our line is correctly going through the data. But we just don't want any residuals that are way, way far off. And again, that's typically going to show that maybe a linear pattern wasn't there. So those are the conditions. All right, now we do have to build that sampling distribution. Remember, this is a part of step 2 in a test, is building that sampling distribution on the assumption that the null is true. All right, so here we need the mean and standard. I really wish we could use standard deviation, but that's actually why this is a t-test, not a z-test, because we are going to have to use standard error. And I'll talk about that in one more moment. And it's the same reason that we talked about it with the confidence intervals as well. So the center of that sampling distribution is the mean of all possible slopes. Remember, sampling distribution doesn't just show our one slope that we found from our one sample. It shows all possible slopes that could be out from all possible samples of the same size. So the center is going to be the null, whatever we heard was true. So if it was the problem where we were told that it was 5 and we want to prove it's more than 5, but the null is that it is 5, okay, so that would be our center. We would center it at 5. But as I just got done explaining, in most cases, we are just truly looking for, is there evidence of a relationship? So the null is that no, there is no relationship, which is a slope of 0. So we would put a slope of 0 in the center. And remember, we're really trying to show that the slope we found is not just a little bit above or below 0. It's really above or below 0, because that would give us that strong, significant evidence that we really want. All right, now we understand, and this is, again, super important that you understand, a sampling distribution is, in fact, a distribution, right? Not every single slope out there is going to be the same. That's just not the world we live in. So some slopes are naturally going to be a little bit higher, some are naturally going to be a little bit lower. So even if the truth is 5, you're not always going to see 5. Or even if the truth is that there is no relationship and that the slope is really 0, like I said, you might see a slight positive slope or a slight negative slope, because it's just the world we live in. Things vary. Now, again, we can't use standard deviation, because we're replacing the standard deviation of all slopes, which, come on, we're never going to know, with S, the standard deviation of our residuals from our sample. And we're using the standard deviation of the X's in the denominator. Now, if you remember from the confidence interval videos that you just got done, you should understand that you don't have to worry about this formula at all. This value, the standard error of the slope from your data, is going to be given to you in one of those computer outputs. So as much as I'm showing you this formula, you're not going to need it at all. So the center of the sampling distribution is typically going to be 0, or whatever maybe you read was true in the problem, for example 5. And again, the standard error is going to be given to you in that table. All right, this is actually done with the setting up procedure. Now, I just want to look at a couple of examples and actually walk through steps 1 and steps 2. That way you can see exactly how this is working out. All right, so here's the first example, and it should sound somewhat familiar. It's the same example we worked with before. We looked at the weights and gas mileage of 12 random cars to find the relationship between the two variables. Below is the data and the scatter plot. So we made a scatter plot looking at the weight and the gas mileage of cars. Now we clearly see a negative relationship. Weight goes up, gas mileage goes down. But maybe there really is no relationship. Maybe we're just seeing a relationship out of pure randomness, pure luck, like it just happened. I mean, you never know. Stuff like that does happen. And that's the whole point of doing a test. That way we can discover, is there really a relationship? So here's everything we need to check those conditions. Residual plot, histogram of the residuals, and that big, huge computer output we need. And here's the question. Does this data give significant evidence that there is a negative relationship between the weight of a car and its gas mileage? Run a test at the 1% significance level to find out. So, like I said, we do clearly see a pattern in our data, but maybe it was just randomness. Maybe it was just a weird sample that we got. So, the only way to answer this question is to actually walk through the test procedure. All right, so step one is that this is a t-test for the slope beta of the regression line between the weight of a car and the gas mileage of a car. So notice I added that context in there. And the null hypothesis is that the true slope beta is 0. Nah, there's no relationship between the weight of a car and the gas mileage. And then the alternative is, no, there really is a negative relationship. The true slope is less than 0. Now, if we go back to our data real quick, we did get a slope, right? And again, that's right here. First column, alphabetical order, A is the y-intercept, B is the slope. There it is right there. So we did get a slope of negative 0.00714. And I'm not saying that that's the true beta by any means. That's just the slope I found. But I want to use that slope as evidence to show you guys that there really, truly is a negative relationship of all cars, not just my 12. And there's clearly a negative relationship between my 12 cars. It's obvious. It's in the scatter plot. I want to show that there's a negative relationship between all cars, weight and gas mileage. All right, so that's the null. That's the alternative. Pretty easy. All right, the conditions are the scatter plot of weight versus gas mileage shows a very strong relationship. Obviously, I mean, it looked pretty good, right? Number 2, the sample of 12 cars was selected randomly to avoid bias. The sample of 12 cars is less than 10% of all cars to assume independence. The histogram of the residuals did look pretty approximately normal with no major outliers or skewness. And the residual plot shows similar variability for each X value. So let's just take a quick look at that. So right here is the histogram of those residuals. And again, that, looks pretty good, right? It actually looks really nice. But again, you're not looking for perfection. You're just looking for no major skewness, no major outliers. And if you look at the residual plot, again, we see positive, we see negative, we see some slightly bigger ones as high as 2.5, some lower ones as low as negative 2.5. But overall, there's not any huge discrepancies there. I don't see any 1 or 2 huge residuals that don't seem to be fitting with all the rest of them. All right, and then finally, I do need to actually build, in my mind at least, that sampling distribution. That sampling distribution needs to be built on the assumption that the null is true. So I am going to have a center at 0. I am going to assume, for the basis of this problem, that there is no relationship between the weight of a car and the gas mileage of a car. And the standard error, again, don't even need that formula because standard error is right here, directly next to the slope in the column labeled SE for standard error. I mean, they're right next to each other. You can't mess this up. So that is 0.00056. Now, once again, I do need to use a t-model. Why do I need a t-model? Because I'm using standard error. This standard error did come from my sample data. It didn't come from all cars because I don't have all cars in front of me. I only have 12. So that is why I have to use standard error here. And remember, when you use a t-model, there are slightly different models depending on degrees of freedom. And the degrees of freedom in a regression analysis for slope is n minus 2, so 12 minus 2 is where I got my 10 degrees of freedom from. All right, that's it for steps 1 and steps 2, so just kind of a sneak peek in terms of what we're going to be doing with this problem. The next video is now we're going to say, all right, now that we understand what this sampling distribution looks like, where does my slope fall in? Is my slope just a little bit below 0, like no big deal, or is it really, really, really significantly below 0? And, so many kids are going to jump to conclusions. They're going to want to jump and look at negative 0.007 and think, oh my God, negative 0.007? That is so small. That is almost 0. There's probably no relationship. But you never know, right? And that's the whole idea that I hope that you've learned in stats is when you have two numbers in front of you, just because you don't think that there's a big difference between them doesn't mean there isn't a big difference between them, right? You just never know, and it all depends on the test, right? And that's why standard error is important. Understanding how things vary is important, and that's probably, if you truly understand this problem, you'll see that the standard error is very, very small. So slopes should not vary much at all from 0. So maybe negative 0.0007 isn't that. You think it's pretty close to 0, but maybe it's really far away from 0. And we will explore that in the next video. All right, let's look at one more example here just to make sure all this sets in pretty well. You may remember this video as well, or this example. We kind of talked about it before. But researchers performed a study where they examined data from a random sample of 16 babies from the United States. For each baby, they measured the age in days of when the baby first began to walk and the average daily temperature in the city of where that baby lived. And they did notice a negative relationship. It's not extremely strong, but it is slightly negative. And it does show that as the average daily temperature went up, the age when the baby first began to walk went down. In the previous videos, we talked about why this possible relationship could be. Warmer weather means less clothes. Less clothes means the baby has a little bit more freedom to move around and maybe could actually walk sooner. All right, so now we have all the data we need. We have our histogram of the residuals. We got our computer output table, which did show a negative slope, right? Our computer output table right here did give us a negative slope. It did show that as temperature goes up, time that it takes the baby to learn to walk goes down. But again, that's the big question, right? Like, is there really a negative relationship or not? So we do have our nice residual plot here as well that we're going to need for the conditions. And here's the question. Does this data provide significant evidence that there is a negative relationship between the average daily temperature of where the baby lives and the age where when baby begins to walk? So we're going to conduct a test at the 5% significance level. So we clearly see well, I don't know about clearly, but we do see a negative relationship. Our computer regression analysis did get a negative slope. So now the question is there really a negative slope? Or maybe not. All right, so step one is, this is a t-test for the slope of the regression line between the average daily temperature of the city a baby lives and the number of days it takes the baby to begin to walk. The null is that there is no relationship. There is no slope. 0 slope. Temperature goes up. When a baby walks, who cares? It doesn't change at all. Doesn't matter. These two variables have nothing to do with each other. And the alternative is what we're trying to show. We're trying to show that there really is a negative relationship here. The temperature really does have a relationship with when a baby learns to walk. All right. So the conditions are that the scatter plot did show a rough linear pattern. It wasn't beautiful, but I did see a linear pattern, I guess. It wasn't a giant curve, at least. The sample of 16 babies was selected randomly to avoid bias. The sample of 16 babies is less than 10% of all babies to assume independence. And the histogram of the residuals, again, was approximately normal. Again, there's only 16 babies here. So when we look at this histogram, we don't really expect to see perfect symmetry, but I don't see any major skewness or any major outliers, okay? So please make sure you understand that. I typically tell students, if you're going to see a major outlier, I'm going to let you see a major outlier, okay? And then finally, the residual plot does show similar variability. Again, we do see positive and negative residuals, but they do seem to be kind of connected, right? There's a big positive and a big negative. There's a couple smaller ones of each. There's similar variability going on there. It's not like there's any major issues going on with that residual plot. All right, and then finally, we do need to build that sampling distribution. So we do have to assume the null is true and that there is no relationship whatsoever. So that puts the middle, the mean of all slopes as 0. If that's true, that should be in the middle, all right? Just because I found a negative slope, I got to keep emphasizing this. Doesn't mean that there is a negative slope. Because, you're allowed to vary a little bit. You're allowed to go down a little bit. You're allowed to go up a little bit. And that doesn't necessarily mean anything. And that's where the standard error comes in. Because that's exactly what samples do, guys. They vary. So that's why we have the standard error. Now, remember, you do not need a fancy formula for standard error like we did with proportions and means. The standard error is right here in our table. Very easy to see. Boom. It's directly next to slope in the column that says SE. All right, guys, that's it. Like I said, in the next video, we're now going to explore finding the t-score, actually locating our slope in the sampling distribution and getting that p-value, and again, of course, making a conclusion. All right, that's it for this video on setting up the test. That's steps 1 and steps 2. Hopefully you understand the big idea of what's going on here. It's really the same big idea we've been working with since Unit 6 when we've been covering inference. It's really all about this idea that just because we see something in a sample doesn't mean that that's necessarily true for the entire population. And that's the whole reason why we have to run a test. All right, guys, that's it. See you in the next video.